So welcome to next part, which is basically position analysis. This part and the next two, which are velocity and acceleration, they should be intuitive for you since you are engineers, and basically the objective of the three parts here is just to give you kind of refreshments, because actually they are very important for robotics in general and for kinematics. Now, position of point actually is determined by reference. So whenever I talk about position in physical space, I need to have a reference, and this reference could be considered the origin of your coordinates, or could be another or any other point in that space. Okay, so the reference is a reference point. Now if we take an example here where we have a reference which is the origin, and if the reference is the origin, it's basically denoted by O for origin, and let's say we have a point P. Now the position of this point in that space with respect to the origin O is represented by a vector RPO. Okay, so this we look here, for example, we have a vector in the 3D Cartesian space. This we just remember because you'll see it now in the next three parts. And if we have this kind of representation, that means we have a vector that is originated at O and is directed at P, or the end is at P. And this here we have, of course, projection on the three axes, x, y, z. And here we have I, j, k are the unit vectors, which they have magnitude equal to 1. And here we have the projection on the three axes. Now we have here the magnitude, which is important, of course, quantity of a vector, which is the norm or the second norm over the square root of some squares. Basically, this is the magnitude. Now there is, of course, a vector is not only about magnitude but also is an orientation, and the orientation or is also called the angular position of a point or a link. Both are valid depending on what you are using it for. Is actually the angle between the vector itself and the reference axis again. So we have, for example, angular position with respect to the x-axis. We could have angular position with respect to y-axis or to z-axis. Now, if we are doing basically, if we are analyzing position or velocity, then you need to have for all of the points, for example, or links in a mechanism, you need to have one reference axis, otherwise you would get confused and also you get wrong results. For example, you take the x-axis. Now, this is the position. Now let's talk about displacement. So what is the displacement? Displacement is the change of position, right? So we have a point P in a space, and I displace this point, which means I change its position. As we see here, from position P to position P prime, so from origin to next position. Now this change or displacement could be linear and could be angular. So linear if I just drag this point in the space, angular if I actually change its orientation only. Now let's look first or talk about the displacement or the linear displacement. It is as a quantity, as a physical quantity, and also as a vector, and this vector is represented by actually here delta rp, and is a vector between, of course, p and p prime, so it's coming from p to p prime. Okay, and the magnitude is, of course, the difference between p and p prime. Now, no, sorry, the magnitude is different, but actually this is how it's represented. Sorry. And here we have the orientation between theta 3 prime and theta 3. That means we have, so this is a link, and this is a link. Now, there is a reason, and basically we will see that more when it comes to velocities and angular velocities and so on, that here we're talking about a point, and here we're talking about the link in general. Because once we do linear displacement of a link, of a whole link, like, for example, if this is a complex link, right? and I did the linear displacement starting from P. So I've actually selected a point or an end at this link, and I displaced it. Now, of course, the other points here, they would have also linear displacement, because if I move one part of the link, then all points would be moved, but they would have different linear displacement, right? So it depends on the position and how I'm moving that link. Now, if I apply angular displacement on a link, let's say this link, then I rotate it with delta theta there, then actually all points on that link would have the same angular displacement. So please remember, this was linear. Each point at that link would have different linear displacement, but with angular, all points would have this same angular displacement, which would be applied on as well the velocity, for example, angular velocity, and also acceleration, like angular acceleration and so on. Now, what is the displacement analysis in general? That means if I have displacement, if I've changed a position of point, which mainly would be driven by, let's say, an actuator, or by, I don't know, by external actuator like human, let's say. But here mainly we are talking about motors, so motor actuators, and these motors basically they displace an object or link. Now the displacement analysis means, okay, if that displacement happens, then let's analyze the new positions of the points on all the links or on a specific link. So this is displacement analysis. And there are different ways to do displacement analysis. One simple way, but it's not the most accurate, of course, is the graphical displacement analysis. And this again, it should be something simple for you. Is basically if I have a link here, which is the complex link, and I have a point B, okay, and let's say I now does kind of angular displacement for this link from position B to B prime with 80-degree displacement or 80-degree angular displacement. What is the new position of point B? And this is the question that I need to answer using displacement analysis. And here we can do it graphically easily, because if I know the dimensions of this link, and let's say I do that rotation, then basically I know the first position of the point B prime. And let's now ask the question of what is the position of point C then, the new position. Okay, now just remember again, if I apply angular or linear displacement, the angular displacement is the same for all parts of the link. The linear displacement is not. Okay, so here I'm also, although I'm applying an angular movement, okay, or angular rotation, that doesn't mean all points would have the same linear displacement, but they would have the same angular displacement. And this is what is happening here. So we applied angular displacement. Then let's say I know the position of P prime, and the question, what is the position of C? And it's basically, if I know the region and if I know B, then I can draw curves here, arcs, by knowing the definition. So it's basically the radius. Then I can draw the first one, the second one, and I get the new position of point C. Okay, and also of course I can previously do the same to know the our previous position of point C. So it's very simple, as I said. If let's say just by drawing these curves or arcs, I can just have the intersection, and I would say this is a new position of point C. Now this is not the most accurate way, of course, and you will see later in the second example as well, because yeah, that depends on how you are measuring it, how accurate your measurement system, for example. This is the another example of a graphical displacement. And here we want to do graphical displacement of a slave link or of a follower link. So slave and follower, they are the same. That means we have a driver and we have slave or follower. So this mechanism, if we see here, it's a closed loop mechanism, right? And we have here basically, so 1, 2, 3 frames, 3 movable frames, right? And we have the base frame that is not movable. So there is here basically the question we need to do displacement analysis. And what we know is that, for example, that the angle between these two is 15 degrees. We know, of course, as we see, the dimension of basically, or the distance between A and B. And here A and B prime. Okay, and basically what is happening there is, let's say that there is an angular displacement of 15 degrees for the driver, which would result in moving B from here to that position along that curve. What would be the new position of, let's say, point C here, because this is a slave. Now, very simple, as we have done before, we know that this is a solid links, right? So the dimension, or actually the distance between B and C, would not change if I'm moving this object or this link. So if I change that, then I can, starting from B prime, draw a curve that represents, or actually that has a radius of BC. This is basically my curve. Then again from here, I know that the distance between C, D also doesn't change. Then I can also draw a curve, and the interaction would be, or the intersection would be C prime. So this would be C and the C prime, okay? So if I applied rotation, that means the point C has moved from here basically to there. Now this is the displacement that happened for point C. They have same angular, no, sorry, they don't have same angular because they are on different links. You remember that? If they are on the same link, they have similar or same angular displacement. If they are not on the same link, then they don't. Now, B and C, you can, no, sorry, actually they are on the same, right? Because they are here. Could be because they are 2 points on the same link. So they would have the same angular, but they don't have the same linear displacement. So the next mechanism here is basically planar mechanism first. And here we have a bit complex mechanism, I would say, because we have the first here, so we have 1, 2, 3, 4 rotational links, I would say, and then here we have the linear displacement or sliding. We do have these dimensions, and we do have the angle there, and we want to do angular displacement. So the question is, as we see there, that the graphical reposition of the links of mechanism as link 2 is displaced 30 degree counterclockwise. So if I basically move this 30 degree, how would that change the whole mechanism first? And mainly we are interested in point E, about actually the linear displacement of point E along this axis. Okay, so we want to see the distance that this point E would move along this axis. Now, all the dimensions of this mechanism are known. The first thing we would do is, starting from the driver, we draw our first arc. Okay, because we know that this is displaced by 30. We know that this dimension doesn't change, so this is our first arc. Then, of course, we can also draw the second arc here. and we draw this line because we know that the movement of this point is along this line. Then the next thing to do, of course, is, as we see there, is starting from this point, is to draw another arc that has basically the dimension or the radius of BC, because this also doesn't change. And this way we actually estimated the new position of point C, which is C here prime. And then from point C, I would now draw the third arc, which is basically had the radius of CE. And then the intersection between this arc and our curve and the line there, this one is the new position of E prime. Okay, so it's graphical, it's quite simple, cannot be applied for all mechanisms, and also is not always accurate. So this is why we need to consider analytical displacement. But before, analytical, graphical could be accurate, let's say if we are using kind of 3D design software. Let's say you are using, as I said, Blender that you use in the lab, or if you are using 3D design or mechanical design like SolidWorks, AutoCADs in general, or Autodesk Inventor, then you can measure angles or rotations, and also you can measure dimensions accurately. So for that you can do graphical analysis, but as we'll see later, for complex mechanisms it becomes hard to do graphical. Now this is why we have the analytical, of course, and the analytical that is used in position analysis, and there are two main techniques. One is the complex polar algebra, and the second one is the trigonometric, basically algebraic law. The most famous one is the complex algebra, but we'll also look at the trigonometric also laws, because also it's quite interesting. Now let's look at this mechanism as an introduction or as a use case for the trigonometric algebraic laws. And here we see that this mechanism, we have an arm, and I want to move this arm, and by moving that is basically forming this motion. Okay, and here we have triangles or trigonometric laws. You can use them when you see links forming triangles, simply like that. If you see links that are forming triangles like we see here, that means we can actually probably apply trigonometric law to do position analysis. Now this is the mechanism. As I said, we can do, or we can draw the kinematic diagram of this mechanism by either lines that represent the simple links like here, or by triangles that represent complex links like this. Now it really doesn't matter how this triangle looks like. It could be wider, for example, but basically what is important, that shows that it's complex and has points, and you are connecting it actually to the middle of that link and not to the end. Okay, so I was just wondering why this is a bigger triangle than this one. That's not important. Of course, what is important is the dimension. If you are doing graphical analysis, it is important the distance between AB and BX, then it's important. Now, looking at this mechanism, so we have 1, 2 that are represented by A, B, B, C. Okay, so this is basically the complex link, and this is actually X, which is this one, and this here is represented by this slider. Okay, and point C is sliding along this blue line. Here we have A as a frame, we have joint, rotational joint, another rotational joint. Here we have a rotational joint, and this is sliding joint. Okay, so we have triangles, or we have the main triangle here. That means we can use trigonometric laws there to do position analysis. Of course, the assumption is that because with trigonometric laws and also with algebraic, in general algebraic laws, we need to solve formulas, and of course always that if you want to solve formula, then the number of basically variable or number of equations should be more equal to the number of unknowns. So if let's say they have, I don't know, 5 unknowns in this mechanism, then it's hard because you cannot get 5 equations, and then it will be hard to solve this formula. Okay. And so if we look here at this formula on the right side, and basically what is happening, we have the mechanism, and we have here our first triangle, and this basically has 30-degree displacement there, or let's say initial position. We know that the dimension between C and B is 40, and between A and B is 50. So the actually question, if I change this angle, so I apply angular displacement, okay, so I'm just pushing this down, what would be the linear displacement of point C? Okay, because if I push this down, this C would move, right? And this is the original configuration, and this is after the displacement. Now, yeah, so they are, there are different laws for trigonometric basically laws, and one famous one of them that is used, which is the sinus or the sine of BAC, which is here is the angle between actually BA and AC. So this is basically BAC, which is this angle, and the sine of this angle or the sinus of this angle divided by BC is equal to BCA divided by, or the sine of BCA divided by AB. Okay, and this is basically known for the trigonometric laws. So the idea, if I have, let's say here, 3 knowns and 1 unknown, then I can solve this formula, of course. So the idea there, okay, let's start with BCA. So because I know this angle, right, and I know this AB, and I know BC, so this known, and what is not known is BCA, because BAC is the original configuration and also the displacement. So I know that now it's 15. And you can use this formula. So basically, let's get BCA, which would be the arcsine of the rest of the formula, and we get, let's say, 38 degree. Okay, and this is the original configuration, so we haven't done any movement yet. So we started by using the 30 degree in this case. Okay, so if it is 30, what is the angle or the orientation of C? Then it's actually 38 degree. Now the question about, okay, this is very simple. If I want now to know what is ABC, then it's 180 minus, it's simple, the sum of the other angles, so it's basically 111. Now the next question is, okay, now the distance between C and A is important for me, which is AC, which is another trigonometric law, and basically it can be represented by this formula. So AC is equal to AB square plus BC square, minus 2AB multiplied by C by the cosine of the angle between AB and BC, so which is this angle. Okay, and doing that we can get the third dimension. So you have a list of trigonometric laws, and you need to look at them basically and see which ones you can use to reach what you are looking for. And the next case here, which is the analyzing geometry in displacement, or the displaced configuration. That means we applied this motion. That means that B has moved and C has moved, of course, accordingly. And basically what's it is the same, just repeat. So we have BCA, B prime, C prime, A angle. So this is the first angle that we need to estimate, then the second angle, then the third. Okay, this is the same, you just repeat it. Now the question is, what is the displacement in this case for point C? It's just the difference between the actual AC or the distance between C and A and the previous distance between C and A, which is the angle or the linear displacement of point C, okay, which is represented by W or C as a vector, because actually this is it is projected over the x-axis, so it's actually can consider it as a vector as well. So as I said, the more common approach is the complex algebra, and of course complex algebra, that means we are talking about vectors in complex space, and the vector, we have seen what is a vector, and we have seen that a point can be represented by a vector. Now the difference is that in complex space, a vector is represented by two quantities basically. One is the magnitude and second one is the orientation of that vector. So it's not like the Cartesian where we talk about the projection on x, y, z. So here we have basically a vector where we have projection over x and y, and we have here the real axis and the imaginary axis. Now it's not that different, of course, if we consider that real axis is x and imaginary axis and y, and we can continue. So we are not here talking about imaginary numbers actually, but we are just using the math of complex algebra to reach, or actually to approach our goal. And if we look in the complex analysis, the vector is given by that, which is, as I said, the magnitude orientation, can be represented also by this form, which is the r of cosine the angle or the orientation plus the imaginary number multiplied by r sine. It's also, you should basically know that basically the imaginary number is basically the square root of -1, and the vector can be described in the polar space as we see here. Okay, is actually, this is the third representation of complex numbers. As we have seen it's actually that you can represent as r multiplied by e, or the exponential basically imaginary number multiplied by the orientation. Okay, so this is actually important to consider, and this is important to consider, and then we can move on. Let's have now another mechanism there. We have here frame, link, okay? And the idea, of course, this is a closed mechanism, it has 1 degree of freedom, and if I move this down, then it will drive the rest, which means this would slide and this would be rotate. Or also if I rotate this, then this would slide and this would rotate. Now we do have triangles here. We can also apply trigonometric laws if possible, but also it's an example of how I can apply the complex algebra, which is also, sorry, there's linear displacement. So basically, as we will see in the velocity and the acceleration analysis, the complex form is makes things much easier. So the idea we have actually, so what we need to start with when it comes to complex analysis or position analysis using complex algebra is that we need to define vectors, and we need to find closed loop vectors, which means here we have triangle, and I need to start with the origin point and draw my first vector in the imaginary or the complex space. Now this vector starts from 0,4 and ends up at here, for example, point A, okay, which is representing that joint. So from first joint to the second joint, and these vectors are connecting joints, okay, just remember that. Now we have the second vector that is starting from 0,4 and at 0,2, And we have the third vector that's from O2 to A. So these three vectors, we should have closed vectors representation. That means basically, for example, in this case, the vector from O4 to A, which is here represented by RA. Now, just for simplicity, the next lectures or next slides, when you see vector represented by only one here element, which is basically A, so which means that you don't see the O there, that's because it's the origin. So if the first point is the origin point, we just ignore it. But here, for example, it's from O2 to A, which is not the origin, then we keep it, okay? Now, what is clear here, for example, in the complex, or actually in vectors also, algebra, that A for RA is equal to A for RA2 vector plus O2 A. So it's basically we have the three vectors. RA is equal to RO2 plus RAO2. Okay, then we have this closed. So now what is known in this case is the distance between O2 and 4. So this is known, which means that the magnitude of this vector is known, which is 9 inch. The magnitude of AO2, which is basically our O2A, sorry, so this always starts from the right to the left, is also known, which is 4.5 inch. The orientation, or which is here, actually the orientation phi2, or phi2 basically here, which is 135 degree, which is no, sorry, this is the phi2, okay, theta, sorry, yeah, this is theta 2, and this is basically the orientation. And what we are doing now, we will use this vector representation, and what we are looking for is vector RA. What we are seeing here, that this is actually known as a vector, and we have two here because for any vector we need two quantities. One is basically the orientation and the other one is the magnitude, and it is known. What is actually unknown is this vector, and we need to estimate this vector. So the idea here is very simple. We start by doing one form of representation in the vector space or in the complex space, which is the cosine sine representation, and we see it as here. So vector RA is equal to RA cosine theta 4 plus complex number A sine theta 4, and here we are RO2 and here are AO2. This actually, as I said, both are known, and here both are known. Okay, so for the RO2, we know that in the complex space it has a 0 in the real part and 9 in the imaginary part or dimension, and for the RAO2 it has -3 in the real part or the x-axis basically, and here 3 point which is basically 0.182 in the imaginary part. Now I want to apply this one just to get to the final, which is basically my target. And yeah, simply we just apply this formula. We know that in the complex space or basically in this representation, the imaginary would be summed with the imaginary part and the real part with the real part, and which means that we're basically doing that here, 0 plus 9. Okay, and here we have -3 plus 3, and so which means that we'll take the 0 with the -3 here and the 9 with the 3, which would end up with this representation of that vector. And of course I can get now the magnitude, and I can get the orientation by basically taking the arctan of y over x, okay, which is basically the imaginary over the real. So this is how, again, we have linear displacement here. So this is basically how we can apply complex algebra and trigonometric laws, and also graphical analysis for position analysis. In the next part, we'll see how to do also how to use actually all three of them for velocity analysis. And of course, next would be the actually the acceleration. Okay, thank you very much, and talk to you in the next